No? Okay. What did we talk about last class? We're talking about. Yeah. Taylor theorem. Yes. What is that? We're primarily talking about. We only talk about this. If you have a function f of x from R to R, that is, let's say, m times differentiable. That means it's also continuous. Okay. And then, and if we know the value of the function f naught means f of x naught. Okay, let me just write it like this. No, let's say we know the function at the value of the function at x naught and its m derivatives. Then and then so on and so forth until the it's not really x naught, x naught plus some epsilon times x minus x naught, and then x naught plus x naught power n. Sorry, there'll be 1 by m factorial. No? What is the confusion? Sorry, yes, I'm okay. Okay, fine. If this is epsilon, that's a symbol I used. Yes, I replaced theta with epsilon. That was a mistake. This will be theta is okay, and then so this is for fine. That's an extension of this. Okay, sorry. Okay, okay. What did we talk about here? Oh, the minimizers of a function. Yes. Okay. Okay. Uh, so we talked about global, local. What is global? So if x is the global minimizer, then what about x? X is any point that is not x star in the domain, assuming the domain for f of x is R. Okay. When is this a strict global optimizer? When the inequality becomes strict, then it's what about local? Yeah, these are things you should already remember. If x star is a local minimizer, then what's the condition? Okay. What is the condition though? Well, whenever you say a local minimizer, you always have to add another qualifier. What is that? Yeah, in what neighborhood? Say omega. This is a subset of R. What is the condition? Sorry. Hey, hold on. So yeah. So if this is univariate stuff. If it's multivariate, then of course this would be Rn, and then this would be it. So there exists an epsilon such that if you consider all points that are less than epsilon distance from x star, all of them will have values greater than x star. If that is the case, then you say, and of course here x and x star belong to well sigma. That's right. Yeah, this is not x naught. Okay. And the simple example. Where is the global minimizer? This is the global minimizer. What about this neighborhood? Okay, let's make it simple. What about this neighborhood? What is there a local minimizer here in this neighborhood? Where is it? It's here. Is there a strict local minimizer? At least the way I've drawn it. Okay. What about this? This is flat. Yeah. So there are lots of minimizers. So any one of these is a local minimizer, but it's not strict. And similarly here, this is the strict local minimizer. Okay. What about this neighborhood? We didn't discuss this, but just out of curiosity, is there a minimizer here? And according to this definition, forget about the definition of first derivative has to be 0, second derivative has to be positive. According to this, is there a local minimizer here in this? Where is it? This point? This one? This one? Yeah, this is a local minimizer. In this neighborhood, this is a local minimizer because that satisfies this. Every other f of x in this neighborhood has a value greater than this. That means this is a local minimizer there. Okay. And then we looked at conditions. The what is the condition? The gradient has to be 0. Zero vector. Yes. So this is all for a local minimum. Okay. What about yes. And right. That simply means it's positive semi-definite. Well, the corresponding single variate univariate condition would be at x star. Sorry. The Hessian is the matrix of derivatives, right? So this is equivalent to saying, so see the second, for a univariate case, the second derivative has to be 0. The generalization of the second derivative in the n dimension is your Hessian matrix. Like the gradient was the generalization of your derivative, f dash, the regular derivative, uh, this thing that we do for a univariate function. That's the derivative of function that maps from R to R. The generalization of the concept of a derivative to a function that maps from Rn to R is your gradient. Okay, so the condition for the necessary condition for uh, a minimum is a local minimum is that the gradient has to be 0. Okay, see this again, all this is only for unconstrained. This would slightly change when we talk about constrained optimization. Okay, what does it mean to say matrix? What is the size of this matrix? Hessian matrix of function mapping from R into N, R into R. Gross N. And what does it mean to say a matrix A is positive semi-definite? Okay, but the general definition, sorry, yes, 0. Okay. Yes, it can be equal to 0 if it's positive semi-definite. If it's positive definite, then it's always greater than 0 if x is not 0. Okay. So the necessary condition is it has to be positive definite, but if this is satisfied, is greater than 0, then this is sufficient. That means if you find that at some point for function f, the gradient is 0 and the Hessian is positive definite, then you know it's a local minimum. Okay. If it's only positive semi-definite, you don't know. And we saw an example for that. For example, if you have the function f of x equals x square, is the point 0 a minimum for the function? It is, because f dash of 0 is 0, f double dash equals 2. Okay. What about x power 4? If you're trying to apply the same condition, dash is 0. Well, it's 0. That means we don't know. At least using this, we won't be able to say. Okay. But we know that this is, in fact, uh, a function where 0 is a minimum. Okay. And then, no. And then we talked about univariate, right? Sorry? Yes, yeah. So we started talking about if you have a function f of x, if you wanted to minimize function f of x, a univariate function, right? We talked about Newton's method, but we'll backtrack and then uh, go through that procedure again and look at a few more techniques, because understanding the univariate method will make it a lot easier to understand what goes on in the multivariate case. Okay. See, barring for a few simple f of x with some relatively simple analytical expression, really solve most practical problems using an analytical approach. So the approach that we often take is a iterative approach or iterative search, okay, where you start with so this is the rough algorithm. You start with a random guess, right? And you call it x0, okay? And then you check. How do you check if it's a minimum? Well, let's assume f dash and f double dash are available to us. Then you check if f dash is, if you're doing it new, let's talk about ideally. If this is 0 and f double dash is greater than 0. Okay? If that is not satisfied, then I say, okay, this is not a minimum. Then now you have to come up with a new guess. Okay. To get the new guess, you say, okay, I'm going to obtain my next guess, which is plus 1. As I'll start from my current point, and then I will do some procedure like this. I'll change my current guess for my minimum, by some value. We'll talk about what this means, and then obtain a new value, and then go back and check again. Okay, and I'll continue this till this is satisfied, right? In an ideal scenario, this is okay, but if since we will be doing this with a computer, of course, this getting an exact zero is not possible. Then you'd say, okay, this is approximately close to zero. You set the limit, 10 power minus 5. If the absolute value of the derivative of the function at that point is, let's say, less than 10 power minus 5, then you say, okay, that's good enough. That's close to zero. And then you check if the second derivative is positive. Okay. This is if this is available to you. If you have access to computing f dash and f double dash. If this is not available to you, then your conditions would slightly change. Then you would do things like, okay, let's say you've run this algorithm a few times. Okay. If you're getting close to a minimum, then each time you update your x of k, the change in x of k should be smaller and smaller, right? Because let's assume here you're using the derivative of the function to do the update, right? If you're getting closer to the minimum, then the change should be smaller. Then you essentially say, well, is my x of k plus 1 minus xk less than some limit, some small number? If this is smaller, then you say, okay, I'm getting close to a minimum. Or you look at the value of the function at k plus 1, f of xk. This is another good way of checking if it's a minimum. Or you check if this is less than some number. These are, I mean, there are different, so there are all these different stopping criteria that you can set up. I'm just giving you a flavor for what this is, but you might find some people might do this. And then they say, well, I'm not interested in the absolute change. I'm interested in the relative change. Is my xk plus 1 less than a certain percentage of my current value, right? You could do the same for f of x. But if xk becomes very small, you run into computing this ratio. So some people might say, well, maximum of 1 comma this. Or maximum, yes, maximum of 1. If xk becomes too small, then you divide by 1. If xk is large enough, then you still do the ratio. So you have all these different criteria that you could possibly use. But the general idea is xk does not change that much, or the function's value itself is not changing that much. Okay. I mean, this is equivalent to saying, well, both of these are equivalent to saying the first derivative is 0. But then you could say, okay, well, the first derivative being 0 only means that it's flat. We don't know if it's a minimum or a maximum. You know that it's a minimum because of this procedure, because you choose this in such a way that f of xk plus 1 is always less than f of k. That means for every successive value of x of k you're getting the function, you're ensuring that the value of the function is going down. That means if this condition is satisfied, you are guaranteed that you've come to a minimum. Well, it could be an inflection point that you don't know, but at least you don't know you're not increasing the value of f of x. That means you're reducing the value of f of x. Now, in the univariate case, we discussed this last time. So if you have a function like this, and if you're here, and this is your xk, one possible candidate for this term. Well, for now, let me just write. Let me not write it. Okay. Just say delta xk. Okay. Some change that we make. Okay. For the univariate case, one straightforward way of looking at what delta xk must be is to look at um, uh, the local behavior of your function f of x at this point xk. Okay, and the local behavior of the function that tells me how my function is changing at the tell me which direction I should be changing my x of k by if I was to reduce this function, if at all it can be reduced from that point. Okay, and that is given by your okay. And okay, well, f dash of xk simply tells you that if you increase xk, how much does my function increase by, right? If f dash of xk is positive, that means I have to increase xk, no? Decrease xk, right? If f dash of xk is negative, that means I increase xk, right? That means I have xk and I have xk. f dash. Right? If this is positive, I need to reduce it, reduce xk. If it's negative, then I need to increase it. Then if I simply do this, right, that will take care of what I want to do. If this is positive, this will reduce. If this is negative, this will increase. And I define this as my k plus 1. Well, you might not want to take a step as big as the derivative. You might say, okay, I want to take some scalar times uh, uh, the derivative of the function at this point. Okay. Okay. Now the question is, okay, now that I've introduced this, right, how do I choose this? Well, we could have started by saying, well, let it just be like this. Okay, and then see what happens. I'll show an animation, and then hopefully that will demonstrate this problem. Yes, I will record it. Yes. Okay. Let's say we are interested in minimizing this function. Okay. If you want to minimize this, and well, I have, okay, I don't have alpha equals 1 there. For now, let's say we do have, we say we want to take some amount of the rate of change of the function at this point xk, and then change my xk by that, right? Now here what I've done, so next question would be, what value of alpha k do I choose? Okay, now what I've done here is I've got four different, well, I've got four such equations with different values of alpha. Alpha 1 is 0, a very small value. Alpha 2 is 0.2, alpha 3 is 0.9, and then I've made alpha 4 slightly larger than 1. And let's say now, using these alpha values and this value that you see here, okay, as the starting point, x0, let's say we go through this procedure of updating my xk iteratively, right? So to this, the very first step I take, okay, what have we seen? Well, the colored dots correspond to these different colored the text here, right? Alpha 1 is very small, so the red dot is essentially moved by a very small amount, which makes sense because alpha essentially determines how large a step do I take in the direction uh, suggested by my derivative. Right? Red moved very little, green seemed to have made a lot of progress. The purple one seems to have made a lot of progress, but it's kind of overshot my minimum that's here. On the other hand, gray seemed to have also overshot. Okay. If I continue this, right, okay, it looks like both green and purple kind of make good progress. Green makes the best progress, uh, essentially sliding along this curve. The purple seems to shoot back and forth. Red has hardly made any progress. So I've done 10 iterations and red has hardly moved any distance. That's because my alpha k is small, right? What's happened with alpha 4? Alpha, for example, so what I'm showing here is the plot of xk. Okay, so all of them started with a value of about 4 point something. For alpha equals 1, this is made progress. Greens actually come very close to the minima. Purple has also come close to the minimum, although it oscillates back and forth. If I continue this, right, green never comes closer. What's essentially happening is the gray, when alpha is very large, okay, you're essentially bouncing off, and you're never converging. And the point to make here is this important. Even though you're using the derivative of the function, okay, to say I'm moving in the direction in which the function reduces. But if you take too large a step or too small a step, you can run into problems. Well, if you take too small a step, it's not a problem. You're guaranteed that you will eventually reach the minimum. But if you take a very large step, then it's possible that, so you're saying at any time I'm going down slope. or in the direction of in which the function is decreasing, you can essentially not converge at all. Okay, and the reason that happens is because the first derivative alone, the first derivative is essentially a local property. Okay, it only tells you the derivative is a good approximation of the behavior of the function only in a small region around xk, because this is the derivative at xk. It describes the behavior of the function well only locally in a small region around xk. But if you have a large xk, right? Large xk means my next point xk plus 1 is arbitrarily far and far away from xk. Once that happens, your f dash of x is not a good candidate for that tells you how the function behaves far away from xk, right? That is why if you make alpha k too large, then this is not a good approach, because uh, the higher order derivatives start to play an increasing role. And to see that, we can actually see that um, from the Taylor series of any function, right? If you have a function f of x, let's say it's a second, right? Let's call it f of xk plus, well, minus alpha k times f dash of xk. Essentially the value of the function at xk plus 1. This will be equal to the value of the function at xk plus uh, xk, and then uh, epsilon plus half. Right? For any general function, there'll be higher order terms, right? If your alpha is large, right, and epsilon is essentially, you can verify this, is alpha k times f dash of x. If your alpha is large, right, that means these higher power terms of epsilon will start to dominate, right? So they say, even though your f dash might be pointing you in the right direction, because these higher order terms dominate, that's why in this particular case at least the function essentially blows up. Because in this particular case, if you, for the x square function, right? Take this. For the x square function, f of xk plus 1 is essentially f of xk. That is this xk square. F dash of xk is 2 times xk into epsilon plus 2 times into epsilon square. Sorry? Yes, that's right. There'll be 1 by 2 factorial. So this is essentially just this. Okay. And epsilon is, okay, if alpha is very large, then this term dominates. That means your f of xk can be greater than xk. Okay. Whereas if this is very small, then this term is a lot smaller compared to this, and epsilon is minus alpha times xk. So this will be k square minus 2 times xk alpha 2 times xk. That means you will get k square minus, no, sorry, this is plus. So this will be minus 4 times alpha k xk square. Means if alpha is small, right? See, this term is positive. If alpha is small, that means the higher order term is gone. The next f of xk plus 1 will definitely be lower than f of xk because of this. If you follow that rule, if you say my next xk plus 1 is xk minus alpha time, where alpha is always a positive number, it cannot be a negative number. Right? So that's the reason why this blows up. That means that for this algorithm to work, the choice of alpha k is important. We cannot choose it to be too small uh, or too big. Too big is definitely a problem because you will not solve the problem. Too small can also be a problem because it will take a long time. And what does it essentially depend on? The choice of alpha k. What do you think? Let me ask you this. If you had two functions like this, one was like this, okay? The other was like this. In both of these, let's say you were starting at some point and you are going to use such an approach. What can you say about the relative choices of alpha k that you would make for both of these cases, both of these uh, problems? Let's say the value that you choose here is alpha. Would the value of alpha that you choose here, would it have to be smaller or bigger than this? Bigger, is it? Why should it be bigger? What does alpha tell me? Alpha is this. Alpha is tells you how much should I change my x by. So remember, this is your xk. And alpha k simply determines where the next xk plus 1 is. This is determined by alpha k. So if let's say I tell you this alpha works well for this problem, and then you come to this problem, and I ask you now, based on this, should we choose a lower alpha or a higher alpha here? Why lower? Right, because if you choose alpha determines how much do I jump next, right? If I jump too much here, then I essentially go somewhere there, right? And if it's quadratic like this with a sharp curvature, then you're bouncing off and not converging at all, right? So the essential idea here is the choice of alpha k depends on curvature of function f of x, f of x at xk. If the function has a large curvature at, at your current point, then the choice of alpha k that you would have to make is smaller. But if it does not have a lot of curvature, uh, then you can choose a relatively larger value of alpha. And curvature, how is curvature quantified? Do you remember what is, for example, if I have a function f of x and I'm talking about the curvature of the function, how do you quantify curvature of a function f of x? Do you remember? So it turns out the second derivative of any function tells you how curved it is. Okay. So here, if you compute the second derivative, you'll have a large second derivative here compared to here. Okay? And in fact, if you have an affine function, or a linear function, the curvature is 0. So if you have f of x, or f of x equals ax, so I don't know if we covered this. This is called an affine function. This is not a linear function. The second derivative, these are 0. That means they don't have curvature at all. They have 0 curvature. So this alpha k depends on, so if you were to solve this optimization problem using a fixed value of alpha k, depending on the nature of your f of x, you can run into trouble, like what we did there. If somebody had chosen an alpha value greater than 1, then that would be a problem there. Right? So, but if I told you uh, an upper limit for the second derivative of a function, so if I have a function f of x, and I tell you that the second derivative of this function, f of x, at any point in its domain is less than, let's say, f naught. Maybe f naught is not a good thing. So it's less than d naught. Could you then use that information to somehow determine alpha? You could, right? If you know that it does not curve, the curvature is not beyond this number, then you can use this to determine an alpha that will ensure that you don't blow up. Okay, so that can be done. Okay, so this can be shown for a quadratic function. If you have a quadratic function, um, x square plus bx plus c, and your interest, let's assume a is positive. If you want to minimize this function, if you choose your, if you were to use a fixed value of alpha, you can verify this later. So if you choose, of course, alpha is a positive number. If you choose your alpha to be 2 times d, 2 times a, to be less than 2 times a, then you're guaranteed uh, to reach the minima of this function using this procedure with a fixed alpha, where alpha is not a function of k, alpha is just a fixed value. Or you make sure that at any given point in time, you don't choose your alpha to be greater than this number. Then you're okay. Okay, so this is going, sorry, of, or if you know that it's upper bound, the second derivative is upper bound by d naught, then this would essentially become, so you never choose k that is greater than that. You can still run into problems here if your function is not, this might not always get you to the minima. So now I'm just going to say, if you have a quadratic function, if you choose alpha k like this, then you will not run into that problem. Okay. The second derivative there was 2, 2 by 2. In fact, there should be a half here. Okay. Because I've chosen alpha k to be greater than 1, that's why it blows up, because it does not satisfy this criteria. Okay. Yeah. So the bottom line is, simple like this works with the fixed value of alpha, and you're guaranteed that your uh, f of xk plus 1 will have a lower value than f of k. That means you lower the value of the function only if alpha k is smaller compared to the curvature of the function. Okay? And in where the Newton's method is great, because what is the Newton's method's iterative approach? You say xk plus 1 is xk minus f dash of xk. Well, the Newton's method says, well, no problem. You can have whatever curvature you want. I'll simply use the curvature at every, if it's available, at every point in my iteration, and I'll use that as my alpha. See, one way, as I said last time, one way to think about this is here, alpha k is simply assuming f dash of k is, f double dash of xk is positive. If it's not positive, then of course the function is not curving in, it's curving up. Okay. So if you use the Newton's method, then there is no problem. Then again, there is no problem as long as this is always positive. Now, in fact, if you apply the Newton's method to this problem, you will find that you only need one iteration. No matter where you start from, if you apply the Newton's method, if you start with any x0 and you apply the Newton's method, you will immediately go to x star. Okay? Because this is, you remember, this is essentially, we got this update equation by saying at any given point, we can approximate a function by a quadratic function. Okay, and then we find the minima of the quadratic function. Well, the original function that you started with was a quadratic function. So the approximation, quadratic approximation for f of x was the function itself. So you are essentially solving the problem in one step. Okay? Where is the Newton's method fail? Okay, when it's 0, and then when it's 0, when does it move away? F dash of x, see, but this is negative though. Is the question clear? Wait, the question is, does the Newton's method always work? Here. This is my update equation. And I know if I move, if my delta xk is proportional to minus f dash of xk, provided I choose the appropriate proportionality constant. If it's proportional to minus f dash of xk, then I'm guaranteed that f of xk plus 1 will be less than xk. That means by taking a step in the direction of the gradient, uh, then I can reduce my value of my functions. That means if this is what is my delta xk, what will happen if this becomes negative? Well, if this becomes negative, then I'm not moving in the direction of minus f dash of xk. I'm moving in plus f dash of xk. That means I'm increasing in the direction where my f of x keeps increasing further and further. So f double dash of xk being less than 0 is a problem for Newton's method. In fact, you remember last time I had shown another example where for a fairly simple problem, the Newton's method fails. Right, this one. Okay. This is the point I start with, right? We find the first derivative, second derivative, and the value of the function. We fit uh, uh, a parabola, and then find the minimum of the parabola, and that's essentially Newton's step. Okay, green is where we started from, and then when we do the update according to Newton's formula, the next point is here. That means it's moved away from the minimum. That's because at that point, f double dash of x1 is negative. That means you switch the direction. So in fact, if you continue this, it'll just continue to move away. It'll never come closer to the minimum. Okay? So even here, f double dash is, all you have to worry about is f double dash. The others don't matter. It's negative, that means it'll still move away. It's gone. Um, but if I start fairly close here, if this is where I start, f double dash is positive, then you're fine. Then it'll solve the problem. Okay? But again, this is not a complicated. This is a fairly simple looking function, and the method fails. That means if you have a more complicated problem which you cannot visualize, there is no guarantee that this is going to work. How would we fix this? Or how can we fix this? If the denominator being negative is the problem. Well, there may be many ways to fix this. One well-known approach. So you keep this and you simply say it's lambda. And you say lambda is some number greater than 0. Okay? Let's say you know the lower limit for f double dash. You know f double dash is not less than some number. Okay. Say d min. As long as you choose alpha to be a number greater than d min, let's say this is negative, right? That means you choose alpha such that lambda is minus 0 is greater than 0. Let's say we know f double dash is never less than minus d min. And if you choose your lambda to be greater than d min, then the denominator is always positive. Okay? So that's one way to fix it. Okay? Let's see if that does fix the problem. Okay? I take the same example. Okay? I've simply put lambda to be 1. Yeah. Start from here. The red is the Newton's method. The second one is Levenberg-Marquardt method. That's the name for the method. Newton's method moves away. Doesn't matter where you start from. The second method, when you add a lambda parameter, at least fixes the main issue with the Newton's method. You can, I mean, I'll again make these available. You can play around with it. You'll always solve it. That's because I've chosen lambda to be large enough. If I had chosen a very small lambda, then there are places where it will fail because the denominator is still negative. Okay, so these are some of the methods that we can use in the univariate case to solve an univariate optimization problem. Okay. Now, if we move to the multivariate case, we will do something similar. See, in the univariate case, our main concern was choosing alpha k, right? We had to choose how big is my step size going to be, because the direction in which we have to move always came from our derivative, right? The direction in which we had to move was in the opposite direction of the sign of my derivative. If my derivative is positive, then I move towards the left. If my derivative is negative, then I move towards the right. Okay, so this we already got. But when you move to the higher dimension, there is a problem, right? Uh, in if you're only dealing with, if you have to search along, there is either moving to the right, moving to the left, and f dash of x told us which direction to move of the two possibilities. But if you're talking about R2, how many, for example, I'm here. There are an infinite number of directions you can move, any of these directions. So that's one. So you have to choose a search direction, and you have to choose alpha k. So you have both these problems now. Okay. So let's say we have chosen this, right? If at any given point in time, let's point in your domain, let's say we are talking about minimum function R, and we are interested in minimizing f of x over all possible x's. Okay. We will again use an iterative approach, right? That means if I'm at some point xk, okay, and let's say I've chosen the search direction in which I'm going to move. Okay, I've chosen one direction. Let's not worry about how it was chosen. Let's say somebody's told us, okay, move in this direction. Okay, and for now we'll assume length of decay is 1. That means it simply tells you the direction in which you have to move. This is decay. Then the next step is, well, the next thing you have to choose is, well, how big a step do I take in this direction? Okay, that is given by alpha k, and we will always assume alpha k is 0, and that will be my next point that I'll evaluate to see if I've reached the minimum. Okay, and the whole point of doing this is this: if you take this step, you have to ensure that your function's value goes down. Okay, means f of xk plus 1 is, okay. So you do this update only after ensuring this. Okay, so in fact, the problem where I showed you that where even for a quadratic function, if you do iterative, if you choose your alpha to be too large, you blow away. Then of course that's not a good. That means you should never do that, right? If you see something like that happening, that means you have to reduce your alpha. Now, let's say for now, let's say we've chosen the search direction through some approach. Then the next step would be choosing this. It turns out that once you choose a search direction, this minimization problem essentially becomes a univariate minimization problem, because you're saying, well, imagine now, well, let me just draw it. Let me draw f of x. These are the contours. That's how my f of x is varying. And let's say I'm here, and someone's given me the search direction. Okay, I know that the search direction I want to take is this. Okay, that means you're saying I'm only going to be searching along this direction. That means along, well, essentially you're not going to be looking back. You're essentially only looking in this direction. Okay, that means this f of x that I have, which is a function, at least in this case, function of two variables, x1 and x2, is now can be thought of as a univariate function that depends only on your position along this line. Okay, it means my f of x, uh, my f of xk plus 1, which is nothing but f of xk plus alpha k times. Now notice xk is a constant, because that's where you are. Dk is a constant because that's the direction you've decided you're going to take. The only variable here is your step size. That means this function here is only a function of alpha k, which is a scalar. That means, let's say I represent this by some alpha k. Okay, how would you obtain, let's say I wanted to visualize this phi of alpha k, how would you obtain it for a situation like this? For a function, for f of x that is a function of two variables, r2 to r. That means this is your R2 space, and then it's essentially a surface, and this is your f of x, and it's essentially a surface. And let's say you're here, and then you've decided this is the direction I'm going to take. Now the question is, the variation of my function, if if I move in this direction, that's my phi of alpha of k. How would I how would I plot it? If you had f of x, let's assume you did have complete access to f of x. Well, you have your surface. Now imagine a plane that is along the direction of dk. The intersection of that plane with the surface would be a curve, right? That would essentially be your alpha k, phi of alpha k. Mm. I don't have a 3D visualization, but I hope this helps. Okay. Uh, right. Okay. The function is this. Essentially, the 2 norm about this point x star. Okay. This is where I am. That's my xk. And I'm showing 3 different dks, okay, in black, red, and green. Now, this is essentially a parabolic ball. This one, whose bottom is located at x star, right? If you want to know how the function varies along this direction, you essentially take a plane in this along this plane that is oriented along this direction, and which is perpendicular to the surface, and the intersection of that plane with this parabolic ball would be your phi of alpha of k, and that's essentially this black curve that you see here. Okay. Now, if you decide to move if you had decided to move in another direction, then phi of alpha of k would look like, for the red direction, it would look like this, and for the green, it would look like this. Now, if you go to another point, you get the same thing. Okay. Well, you can also change it now. Depending on which direction you choose, you have a slightly different profile for the way the function is varying. Okay. So this is for a parabolic one. Now, if you do a more complicated one, well, slightly more complicated, instead of a symmetric bowl, let's say you had a asymmetric bowl, but still parabolic. Then the width of the parabola in each of these directions would be different depending on the direction in which you move. For example, here, in the black direction, the parabola would be wider, whereas in the green and red direction, the parabola is much more squished. That's what you see here. The black parabola is broader, whereas in these two directions, it's a bit more squished. this function, this is called the Rosenbrock function. This is, I mean, if you can look at the expression, this is kind of a test function that people use for testing minimization algorithms because it's very badly behaved. Uh, we'll come back to that later. It's just very, if you do, I mean, this is a good way of testing naive algorithms, which will perform very poorly with this function. Here again, if you're at that point, the function has very different profiles depending on the direction in which you look. So then once you've chosen, I mean, you know you are where you are now, xk, once you've chosen dk, then the next step is you want to choose this alpha k so that this function is minimized. Right? So at solving or optimizing a multivariate function like this, once you choose a direction in which you want to search, your problem now becomes that of solving a univariate problem like this, okay, where alpha k and 0. Okay? You choose a direction, you solve this univariate problem, and if you solve this, this will give you some alpha k star. Well, I should really say argmin. If you solve this, it will tell you the best possible or the step size that you have to take in that direction for you to reach minimize this as much as possible. Okay, and once you have this alpha k, you plug this in here, and then you take that bigger step in that direction. And then in this new position, now you again have to make a decision on which direction do I choose. And then once you've chosen the direction, you will have a new phi of alpha of k, and then you repeat the same procedure again and again. Okay, so the story essentially is, if you have a multivariate optimization problem, at each stage you essentially are solving a univariate optimization problem. Okay? And the same issues that we saw earlier in the choice of alpha come back to haunt us, right? How do I choose for example, this is a univariate problem. Uh, that means now I still have to choose an appropriate alpha that will solve this. Okay? That means now the way you would solve this, so now your phi of alpha k is univariate function of alpha k, and then you want to find the value of alpha k that minimizes alpha k. And if you plug that alpha k here, then you're guaranteed that f of k plus 1 will be lower, and as low as it can be made if you decide to move in that direction. Okay, so sometimes, or this type of a procedure, where at each step you are searching along a particular direction, is given a name. It's called a line search, like that, where you're essentially saying, well, I need to search for the best possible step I need to take, or the best or the optimal step size I need to take along this line. Well, if that were the case, if you search along a particular line, the best thing to do would be to precisely solve this using a numerical approach to get the best possible value of alpha k star. Okay, it turns out that you actually don't have to solve that very accurately when you're solving multivariate problems, as long as you or inexactly solve it, in the sense that as long as this alpha k that you've chosen ensures that the value of the function actually goes down, you're fine. Okay, so often we will never, you won't do an exact search. You know, such. So you will not spend a lot of your resources trying to solve this exactly. You solve this inexactly, jump to the next position, because your ultimate goal is here, right? Jump to the next position and then solve that again inexactly, and then keep moving in Rn. And it turns out in practice that works pretty well. So often you will never solve this exactly, and inexact solutions are pretty okay. Okay. Now, because we are talking about a univariate function that we are trying to solve, right? Um, and you have phi of alpha k. What people will do is they will choose an initial value of alpha of k that is very large. Okay? You choose a large value, and then you see if I take that big a step along the direction dk, what is my new well, hold on. Here. Let me write it like this. Okay. Phi of 0, what is phi of 0 according to that? This is just this. This is the value of the function where you currently are. Okay. What about phi of alpha of k? Well, that's the next point that where you would reach if you choose a value alpha k for in that step set. Right? So what people would do is this: they'll choose a large value. Okay? Let's say some alpha. Okay. You then plug it into this, and you find out the value. You find if this is lesser than this. Okay. Then, well, less than for now. Let's say less than. If it's lesser, then you're done. You have a value of alpha that will ensure that the next value of f of x k plus 1 will be lower than f of x k. Then you're done, and then you simply then move to x of k plus 1. If this is greater, right? So this is the first step. If this is greater, then you say, okay, we cannot exit now. You say my new alpha is is let's say some alpha k. Tau is a number less. You take a fraction of your alpha k and assign it as your new value for alpha k, and then you compute this again. Okay, let's say initially this was alpha max, and let's say I choose, sorry, let's say I choose this to be alpha half, right? I start with this value. If I take that big a step, the value of my function at the new point is larger than where I am now. That means I should not be taking that big a step. Okay, then you come down and you halve the value of your step. Okay, and then you go and check again, and you continue to halve until this is satisfied. And the moment this is satisfied, you return this as your value of alpha, or the step size that you need to take. Then you've essentially kind of roughly solved this. Then you can do this and then jump to the next one. Okay? That's one way of doing this. And this is often used, and this is called backtracking. So if you see something like this, you know what they're doing in terms of decide how they're deciding the step size by essentially choosing a large value first and then reducing it progressively until they are able to lower the value of the function, and then they jump, and then they keep doing that again and again. Okay, so this criteria that you use, this is okay to start with. There are other criteria as well that can give you a better value of alpha than using just something like this. These are there in the slide, so you can refer to the slides for slightly better approaches than this. Okay, so what we've seen so far in multivariate optimization, you choose a direction, you decide on well, you're at some point you choose a direction, and then you decide on your step size based on some procedure like the backtracking approach, and then you simply then keep searching. Okay, I will stop here. It's already time. Um, yeah, and then we'll think. Well, you guys don't have anything after this. Okay. Let me continue for another 15 minutes, and then we should be almost done. Right. Now we at least, this backtracking idea, you can of course use it in your univariate case as well. So this is applicable for the previous discussion that we had. Right? Okay. So now we know, at least we have a way of choosing alpha k appropriately. Next question is then, okay, this. How do I choose my direction? Okay. See, before that, the Taylor theorem that we talked about, I only talked about the univariate case. There is a multivariate version as well. So if f is a function from R, let's say it's at least differentiable twice. Okay. Then this let's say you know the value of the function at x naught, you know the gradient at x naught, and you also know the Hessian x naught. Then this function can be written as and then the higher order. This is the um, multidimensional equivalent of the Taylor's theorem that we saw earlier. And this will become handy later on. Now we'll come back to the question of, okay, what direction do I take? Okay. Now we saw that if uh, you move and you decide to move in this direction, D, right? Uh, you can move. Let's say you can freely move along this line. Okay, that means, and let's say this is some point x naught. Okay. The way the function varies along this line uh, is given by no, sorry, that's not what I wanted to say. Say you're at a point x naught. Okay. Now we have to decide on a direction that we need to choose. Okay. Well, the direction that we need to choose should be kind of obvious. You choose the direction in which the surface goes down. Okay. There are different directions you can take. Right. Now, if you ask which is the direction that along which my function goes down the most, to turn out that that direction is essentially this. Okay? This can be shown as well. You can compute what is called the directional derivative. That means if I were to move in this direction, how does my function vary? Because if I choose the direction in which I'm going to move, it's a univariate function. That means I can simply compute the derivative of that univariate function. Right? Similarly, if I choose another direction, I can compute it's again a univariate function. I can compute the derivative for that. So I have a univariate function in any direction that I choose, and I can compute the derivatives of each of those functions at that point. I will then choose the function that choose the direction along which the function varies the most. Okay, or the rate of change of the function in that direction is the fastest, and that direction is essentially the gradient. Okay, and the gradient tells you the direction in which the function increases the fastest. Okay, and if you want to reduce, that means we need to move in this direction, and that is one possible choice for um, choice for decay. I say one possible choice because it turns out that the gradient is not always the right direction to move. Okay, there are other directions uh, again related to the gradient that are better than the gradient alone. Okay, that means we are then, if that is the case, let's say we are going to do just use the gradient for now. That means one possible approach is I'm going to write xfk gradient of fk, that simply means the gradient of f at xk. So this is one possible approach. And again, now using backtracking, or well, I choose some fixed alpha, or I use backtracking to choose some alpha. I should be able to then, well, minimize my function using this approach. Okay? So we'll see some examples of what would happen if you do something like this. Right. Okay. Let's say we well, the problem is minimize this function f of x. We're going to use an approach like that, a simple gradient descent, and I'm choosing a fixed value for alpha 1. I don't know if you can see it. I fixed alpha 2.025. Okay, I don't know if this is large or small. Okay, if I do that, my current value is here. And this is the value of my function. And here I'm essentially going to be displaying I think the distance of this point from the true minimum. If I do this, well, at each point, it's taking a small step towards the minimum. And if I keep running this, initially you saw that it was moving relatively fast, but as it gets closer and closer, it seems to slow down. Right, I'll stop here. It'll eventually get there. Okay. Why did it do that? Why did it move fast initially, and then as it got closer and closer, it started to slow down? And that is the approach we're using for doing for here to solve this optimization problem. Why might that be? Alpha k is constant though. I fixed alpha k too, so this is fixed too. Well, this one, it depends on two factors, right? It depends on alpha k and also this. And as you get closer and closer to the minimum, what happens to the gradient? Well, at the minimum, it's zero because we are talking about a continuous function. Of course, it cannot be a large value and then suddenly go to zero at the minimum. That means that the gradient also has to gradually get to zero. So as I get closer and closer, the gradient also goes down. That's why initially it looked like it was making large steps. But as you got closer to the minimum, it started making smaller steps. Now, if I change so I'll increase, I started with 0.05. Let's say I increase it to, let's say, 0.2 or 0.25. Well, 0.3, it's fine. Now you see it's much better. Well, I've almost reached the minimum in about 15 steps. I can keep doing this. I can keep increasing it further. What will happen if I go beyond a certain point? I don't know if this is going to blow up. Well, sorry. Sorry, I should have had a larger change every step. 1.3. Now you see it's essentially overshot and then comes back and forth. Now you can imagine instead of 1, if I had made it 10, it would not converge. It would simply just bounce off and then move away from the minimum. Okay? So that's for this. And what else do you notice? Let's do another one. In terms of how this is moving towards, what else do you notice about the trajectory of this, of your solution? Well, at each point, it seems to cut the contours at right angles. In fact, that because we're always moving in the direction of the gradient, that's a property of the gradient. I don't know if you remember when I said last time, the direction of the gradient is always orthogonal to the contour. That's why it's always perpendicular. Now, if I choose a different function, something like this, something similar, but the behavior is slightly different now. It is not, earlier it had a straight path, whereas here it seems to have a curved path. But again, at each point, the constraint is the direction in which you move is always orthogonal to your contour. Since that is the case, that's why you have this curved path, because now you've got ellipse. Um, your contours are now, or level sets or contours are now ellipses. Right. This is the two-dimensional equivalent of this example that I'd shown earlier, where this is 1 minus e power minus x square, where if you did the Newton's method, you started here, you moved away, whereas if you started close enough, this is the two-dimensional equivalent of that. Right? If you don't use Newton's method, if you simply do simple gradient descent, of course you always get to the center. Of course, it's slow because your gradients are small, and my step size is very, very small. This is that crazy function, the Rosenbrock function. Yeah. I started here, my alpha is too big, it just blows up. Okay. If I restart again, then I reduce my alpha to a very small value, then it seems okay. But here is the problem with the This is why the Rosenbrock function is a problem. If you're so there is essentially a curved valley. Here, so this is the valley. There is a clear minimum. This is the minimum, and there is a curved valley. But in one direction of the valley, the function is very flat. Okay. Whereas on the other, so that's in this, let's say in this direction, it's fairly flat. On the other side, it's really sharp. Okay. That is why here, when I was here and I chose a step size of 0.008, even such a small value led to a large jump on the other side of the, I essentially jumped across the valley, right? The first step, the second step, and the moment I hit the valley, then you see my progress is really slow. That's because along this direction, the function is really flat. Your uh, your gradient is very, very, very small. Whereas in this direction, the gradient is huge. Okay, yeah, this will take forever to converge. Okay, so if you do gradient descent, so I mean, you of course have. I'm not doing backtracking here. I'm fixing alpha k. But if you did backtracking, then of course then you might not have the problem of blowing up, because you will always choose an alpha that will always ensure that the new value of the function is lower. Okay, I think I have. Yes, I do have it with backtrack. Okay. That's the fixed alpha k. Okay. Now let's say we were not doing fixed alpha k, but we are getting this through backtrack. Okay. That means with the Rosenbrock function where it just blew up, that should not happen, because you're choosing your alpha at each step. Your alpha is now adaptive. Your alpha is always chosen so that the value of the function at a new point is always lower. I mean, I'll have to explain what's going on. Right. I'm here. Earlier, remember I chose here. I've said alpha naught is 5. I choose a large value for alpha naught. Earlier, remember when I chose an appropriate value, it simply kept moving along the line till it reached here. Now, when I do backtracking, I started with 5, but then it chose a value of 1.25 because it started with 5. This condition was not satisfied. So it went and halved the value of 5 to 2.5. Check this again. This was not satisfied. It halved it again, 1.25. And this condition was satisfied because it said, okay, if I take a step of 1.25, the value of my function goes down. So I'll choose that as a good enough solution. So it jumped there, and it'll do that again. It'll make another jump. Now 1.25 seems like a good alpha. So it's already reached the minimum. So that's with this function. Well, let's do this. There. It's no different from the previous case, except that at each point your alpha k could be different. So it is different, 3.125. Well, 0.3125. Okay. Earlier, you remember when alpha was small, it made a smooth curve towards the center. But now you're choosing a large enough alpha so that you're making faster progresses. Just because you're doing backtracking, because you're saying I'll start with a large value and then get the largest value lower than alpha, my initial value, that reduces the value of my function. Let's look at the Rosenbrock one. Now, no matter where you start, so remember alpha, when I had an alpha of 0.025, if I had started at this point, the function would fail, it would blow up. Okay. But here I'm starting from 5, but I'm doing backtracking. Okay. The backtracking will ensure that you don't blow up. It'll get you to the valley. But once you get to the valley, if you're still only doing gradient descent, you are now at the mercy of your gradient to move you in along the valley, because the valley itself is very flat in one direction, whereas in the other direction it's very steep. So here it'll essentially take forever to get to the minimum, even though you're really there. All the other ones are similar. Yeah. You've gotten rid of the problem of having a very small alpha essentially by doing backtracking. Okay. All right, we'll stop here. Then there are a couple of more things: generalization of the Newton's method and the Levenberg-Marquardt method, and then we're done for uh, unconstrained optimization. Are there any questions, Bill? So far? See, we will release the slides and these programs. If you're not able to run them on your, how many of you use Python or have Python installed in your computer? Okay, at least for the sake of this, please install to be able to run this. If you have any trouble, maybe Sujit can then help you to get it to run on your PC. Yes. So you make a figure and then you attach a callback for a keyboard event. That means every time I press, it'll call a function that will update the figure. That's all. Yeah, I'll share the code. You can look at what done. It's standard procedure. I've copied it from somebody else. You can copy it from me. Okay. Okay. All right. Thank you.